Alrighty, everyone. So I'm Guillaume. I'm the founder and CEO of Extropic. Today I'll be talking about the future of computing. We've been working on this for about 3 years now. To me, this is the most important thing I could be working on for competitiveness with China, and it's the reason I left my job in quantum computing at Alphabet to pursue this paradigm of computing from scratch. And we've made a lot of progress, and it should be on everyone's radar. The numbers I'm going to showcase today are pretty surprising, but everyone's welcome to come talk to me afterwards. So I'll just stay here. All right, so generative AI is eating the world, as we know. The models are getting exponentially bigger over time. The reason we're using more and more computing is because to train these models with more and more parameters, they need more and more compute, more and more data in order to scale in terms of their performance. But the rate at which the demand for compute is scaling at a rate that is exponential, that is far outpacing Moore's law, even at its peak. And the reason is, as you scale how many flops, how many floating point operations you do during training, and the size of your model, you get more performance. You get more intelligence, more value. And so there's no real limit in sight other than the sort of soft limits of the practicality of building a ginormous supercomputer and powering it. Right? And so everybody, you can make these extrapolations. A couple years ago, even at GPT-3, we were seeing an exponential trend in the power requirements to train these models, and now people are building nuclear reactors, investing in nuclear fission, nuclear fusion. So if we're doing particle physics to power these AI supercomputers, why don't we do particle physics to figure out how do we execute these algorithms, using electrons? And that's what we set out to do. Unfortunately, in order to densify compute with today's approaches, Moore's law is basically dead for deterministic computing. It doesn't matter how you cut it. We're hitting the top of the S-curves for various parameters. If you look at the scaling we have right now, by early 2030, we're basically out of luck. We're going to reach a point where our transistors get too small, and the thermal fluctuations of matter affect how electrons flow through the transistors, and that causes big problems for a deterministic computer because your transistors misfire. And we call this the thermal danger zone, so we're on a collision course for it, but really we're still many orders of magnitude far away from the fundamental limits of computing and thermodynamics of computing. And so is there a way to do something better? Well, we can think about taking inspiration from the brain, which is a supercomputer for AI with running models of 100 trillion parameters using 20 watts in 1 liter. It's pretty amazing. That's about 100 million times greater energy density and efficiency than our GPUs. And so if we want to take inspiration from nature and take inspiration from biology, do we get obsessed with biomimicry and create a plane that flaps its wings? No, we understand the principles that biology has learned to harness, and we harness those principles directly using artificial devices, so like the airplane. And so that's what we're doing with our approach to computing. Really, what we identified is that the type of physics in the brain and in many self-adaptive complex systems, including our cells and so on, is mesoscale physics, so out of equilibrium thermodynamics. So this isn't your great-grandfather's thermodynamics. This is the stochastic mechanics underlying biology, the physics of jiggly matter, right? So it could be electrons jiggling, it could be matter jiggling, and it's actually not quite classical, so it's not deterministic, and it's not quantum, so it's not a superposition of different states. So it's a probability distribution over different states of the device, which is really weird because we're used to having a computer that's in a deterministic state that we know and control, or nowadays people are getting used to quantum computers which are in a quantum superposition. But we're doing something in between, which we think is much more sensible and much more scalable in the near term. And ultimately, if you look at where algorithms are going, algorithms want to use more compute. They want to use more probabilistic primitives. Deep learning has gotten us pretty far, but as we saw, just a single forward pass of a deterministic function, like in deep learning, you have to make the network bigger and bigger and bigger if you want to capture more and more complexity of the world. So for example, if I'm predicting the weather, if I'm trying to predict a tail event that's not like the typical, typical weather, I'm going to need a huge neural net to capture that tail event. And as I scale up my neural net, I need more parameters. And then to train those parameters, I need more data, right? And so what we're seeing instead is using more probabilistic behavior in our algorithms to save on data and save on parameters and save on training compute. So algorithms are actually converging onto a type of algorithms we call Monte Carlo algorithms. So for example, if you use O1 or O3 or reasoning mode in your AI, it's searching over the space of responses a bit like the AlphaGo algorithm searched over, moves for Go. And what OpenAI and Google have shown is that you could just scale up how much test time compute you use, so how much thinking you do at test time when you're using the network, and train a much smaller model and still have much more performance. So our prediction is that test time compute is going to scale massively and kind of leave sort of training scaling as sort of far less relevant. And so the most general form of these algorithms are called Monte Carlo algorithms, and they're as old as computing itself. They were cooked up during the Manhattan Project, it's very challenging to do these algorithms on a deterministic computer because you're trying to generate randomness at every time step using a classical computer, which again doesn't have native randomness. So it just does so through highly complicated functions that are really energy inefficient. And the goal is usually to have these walkers walk around and do little updates, and eventually the average sort of walk, if you take a sort of shadow over time or if you take a blur, gives you a certain distribution. That's your target distribution. And in machine learning, that distribution needs to be data. And so that's how Monte Carlo algorithms work. They want to achieve equilibrium or detailed balance. And essentially, we're building a substrate to run these algorithms, and we think it's going to be the densest substrate from first principles for artificial intelligence, and that density is in terms of space, time, and energy. I'll show you why. My personal mission is to scale, we got to scale the wattage of civilization. We got to scale also intelligence per watt. If we scale both, we scale the amount of intelligence in our universe. But, at the American level, if we have more watts in America and we have a better way to convert watts to intelligence, then we have massive prosperity and competitiveness with China. Trevor and I, co-founder, CTO, we built TensorFlow Quantum. So originally we brought AI to quantum computers. We got poached straight out of school by Google. I went to work at Google X, worked on quantum sensors, internet, and so on. But over time, ended up getting sucked into thermodynamic computing and trying to pioneer it. We're building hardware, middleware, and software. So how to compile programs, software frameworks that plug into current day deep learning frameworks, and the hardware itself. This is slightly technical, but our primitives are something called energy-based models, which are, won the Nobel Prize in 2024 for physics with Geoffrey Hinton. They're kind of the ancestors of neural networks. They're more general, and we think they're more expressive, and we could run them essentially natively in our hardware with extreme energy efficiency. And so we decompose programs into these energy-based models. The beauty of these is that you could train them. So if you have essentially, you could think of it as we have a parametrized bowl that we can sort of tune the shape of this bowl, and we have electrons dancing in this landscape. And as you saw earlier, when you let the electrons achieve sort of detailed balance, right, when the flux kind of stabilizes, essentially you get a certain distribution, and you can train by contrasting hallucinations with reality these energy-based models so that you essentially are doing AI as pure electron diffusion physics directly in hardware. So it's as energy efficient as you can get and as fast as you can get by the laws of thermodynamic control. And so to me, there's an urgency to have a Manhattan project for AI, and we're essentially the closest thing to that, but we're a private startup. And so what sort of applications can you look at? Obviously, it's very disruptive for finance. It's a huge advantage if you can do Monte Carlo sampling much faster, much more energy efficiently than your opponents. If you could think faster than your opponents, I don't have to spell out how that's disruptive for defense and warfare and robotics. And of course, if you're in generative AI, to scale your models, you need to use this. Another aspect that I haven't covered much, but essentially simulations of biology are about to have their GPU moment with our hardware. The speed ups are 1,000, 100,000x plus for simulations of biology. And so, in terms of bioweapons, defense, or offense, it's a very disruptive capability. Where do we start? So originally we started with quantum computing hardware. We heated up. We showed we can control the electron diffusion and train these energy-based models. We have a whole portfolio. There's a movie on YouTube if you want to check it out. This is our first gen hardware. It was superconductors. It had 3 probabilistic bits on it. And if you were to scale this computer to be like, occupying a whole room, you could run a transformer on it, and the energy efficiency gains you get are up to 100 million x. So that was really encouraging, from our calculations and fitting our calculations to data. But of course, it's superconducting, and it's in a big fridge, so it doesn't scale. So what we set out to do since then is figure out a way to port this technology to silicon and figure out how to run it at room temperature so that we could put it in every device at the edge, in the cloud, and densify it massively. And so about 1.5 years, 2 years ago, we set out to go all in on silicon, and we had some projections of how it would run at room temperature. And so we actually manufactured the chips last year. I have one right here. So this is the first gen silicon room temperature thermodynamic computer right here. And we're within 1 or 2 orders of magnitude on this plot from our experiments, which we've confirmed internally in our lab in Boston. It was covered in Wired recently. Essentially, this technology is no longer theoretical. It's right here. We have it in the lab every day. We have it under control. This is a very disruptive technology. It massively changes everything. It changes the whole game theoretic calculus for scaling energy, for the supply chains for AI chips. We can manufacture these chips in America. We did a batch with Global Foundries recently. We can make them in the US and still have the best chips in the world by far. So what sort of energy efficiency gains and performance gain can we imagine? So this is a test chip, and we're going to put it in the hands of customers in the coming months. But what if we were to scale up this chip? What's stopping us? Well, there's nothing stopping us, really. It's just time. So we are scaling our number of probabilistic bits and probabilistic compute elements. So I showed you the first prototype was 3 probabilistic bits. This one has about 300 probabilistic components. Our next chip has 1 million probabilistic bits, right? If you hear someone talking about quantum computing, they want to hit 1 million qubits by 2035. We have this chip internally by end of year, right? So it's a very disruptive capability. And the reason we can do this is because we're using silicon. There's really advanced fab technology. There's no bottlenecks to scaling, and so we're scaling with urgency. But we're aiming to make the chip available commercially next year. So what does this mean for algorithms like in AI? For example, if you're running a diffusion model, such as image generation, video generation, a world model. Nowadays you have discrete diffusion like Gemini diffusion. What sort of speed ups can I get if you replace your simple primitives that were made for traditional computers with energy-based model primitives that fit on our hardware, you can use 100 times less steps, and the full end-to-end benchmark, performance gain is pretty massive. So DDPM is a diffusion model, so it's the state of the art. DTM is denoising thermodynamic model. It's our proprietary models and running on our hardware. The gap is very massive, and this is a simulation of a chip that we have on hand by end of year, and it's only 1,000th of the chip. So this makes, export control on GPUs and all these other types of computing literally irrelevant. And it makes all this narrative of to scale AI, we're going to need nuclear-powered data centers. Yes and no. I think if we have a way to convert energy into value that's much more efficient, there's going to be more energy demand, so I'm not going to dissuade people from scaling up nuclear, but the density of how to arrange data centers, this violates a lot of narratives. So anybody who's a stakeholder approving budgets for $500 billion build-outs for data centers needs to know about this technology. So when will the first devices be ready for early access for enterprise, government, and so on? Well, we're, as I said earlier in the talk, we're aiming to have it available summer 2025, so by end of summer. So please reach out, sign up for the alpha, hardware alpha on our website, and potentially email me if you're interested, or come find me during the Expo. Thank you very much. All right. I think I have 3 minutes left. Questions or, yeah. Oh, that's, well, so EAC to me was a way to fight sort of demoralization, psychological operations. It was a viral optimism as a sort of psychological immunity for the masses, right? And we scaled it, and the goal there is to climb the Kardashev scale, which is, the energy consumption and production of civilization, and we think that's a golden metric to aim for in terms of, culturally, what our culture should aim for. So it's anti-degrowth, if you will, yeah.
I'll go quick. Hi. Two very quick questions. One, which process did you use at Global Foundries? Second, more to the point, you say you get around current export controls, but you're delivering a different type of IP. So can't commerce just come along and say, right, your IP is now subject to export control?
They could, right? And we're happy to talk with the administration of how to deal with this technology. Obviously, we don't want it to get in the hands of China anytime soon. And personally, having been at Google and having our IP be cloned within months in quantum by China, left a chip on my shoulder. I won't say which process we're using with Global Foundries. That's too confidential for now. But it's nothing too esoteric. Maybe we could chat offline. Yeah. But that's right. Legislation just needs to adapt. I'm just trying to put this on the right radars. I think this is a huge competitive advantage for the situation we're in. It's the competitive advantage. It's why I burned all the boats. It's, I was very concerned with our competitiveness with China for AI, and this is the project. We're a bunch of MIT, Harvard, Waterloo folks in Boston. We literally treat it like a Manhattan project. We could use help. We could use partners. We're going to raise more capital. Silicon Valley's excited about this, but I also want to put it in the right hands for defense and government work as soon as possible. Yeah.
Is your technology, or what are the efficiency gains? Is it appropriate to use your technology to render massive LLMs? And if so, I kind of understand what's going on with GAN and machine learning and very application-specific, data-specific types of problems. I understood your charts, and I could see these really, really, really big gains. Sounds amazing, huge markets. But for the rest of us, I'm curious, if you wanted to compile the biggest llama model, for example, render it, would you get serious efficiency gains on your stack?
Yeah, I mean, technically we can port over existing models. We're still benchmarking. So we had a benchmark with superconductors. We're figuring out a benchmark for our next chip for, let's say, a llama-like model. What we showed was a diffusion-like benchmark for now. We're still working on more benchmarks. We're only 20 people at our company. But in general,
I mean, maybe that's not what it should be for. I'm just
I don't think
what it's.
I think for optimization broadly, for perception, control systems of all kinds, guidance, robotics, cybernetics of all kinds, there's uncountably many benchmarks we could do, and really we just need to get this technology in the right hands as soon as possible for people to figure out the advantage
so like
they get.
Computer vision and object detection, surveillance,
in
observability.
General,
yeah.
I think 1000x for most things is kind of the floor, but if you optimize the algorithm for our processor, sometimes you get much deeper. You get 100,000x plus, right, in terms of energy efficiency gain and speed up. So it's very disruptive. Again, there's a coevolution of hardware and software, and we need the software to adapt quickly for our hardware. Alrighty. Well, thanks everyone. I'll be around rest of the day. All right. Thanks.